All right, I know everyone's in here. Everyone's paying attention. No one's staring at their phone right now. Edgar. Okay, so let's go ahead and do these notes. So class. Yes. Thank you very much. So now no one in here has their earbuds in because they are paying attention right now, aren't they? Thank you very much. Good job. All right, so now this is actually going to be pretty easy. It's so easy, even Oscar could do it. But Oscar would have to put his phone away for him to pay attention long enough. So, Oscar, could you please do that? Yes, thank you. All right, so for everyone that's now finally joining us online, okay, we are on 39. So please don't try and do the homework while we're trying to do this because you're going to miss all the instruction. There's like 3 or 4 people that try to do this. Yes, good job. You get the homework done, but you have no clue what we're doing. So please don't do that. So right here, path and circuit. So now previously, we've been talking about Euler. Euler has to do with edges and all the roads and covering all the roads. Now, Hamilton has to do with all the vertices this time. So it's like going pizza delivery. So let's say AJ is delivering pizzas. Okay, is AJ going to make sure he drives across every single road in between here and his pizza delivery? No. He's going straight from here to where he needs to go, right? That's important. That's the difference in between this. Where the Euler, we had to cover all the roads or all the edges. Now, with Hamilton, we're covering all the locations. We don't have to take all the roads. So a path passes through each vertex of a graph exactly once is called a Hamilton path. If a Hamilton path begins and ends at the same vertex and passes through all other vertex exactly once, it is called a circuit. So we have path and circuit. Remember, circuit always goes back to the beginning. Now, find a Hamilton path for the graph. So let's go ahead and start off with A. So we're going to deliver some pizza here. So if I'm starting at A, letra A, are they ever here? So at least pay attention while you are. Need something to write with? Okay. So we're starting at A. If this is a path, do I end at A? Say no. I don't end at A. I can end anywhere. But I'm going to do a path. So I'm going to go A, B, C, E, D. A, B, C, E, and D. I go to all the locations. AJ, did you deliver all the pizzas to all the different houses? Yes, you did. Did you have to take every road? No, you don't want to take all the roads because that means you're wasting gas money. And pizza delivery guys have to buy their own gas with the money that they make from the right there. So now let's change up the colors here and let's go this way. Now this time we're going to do a circuit. So if it's a circuit, what do we know about circuits? That it has to end where it starts. Very good. So let's just change it up because I'm going to go A, E, B, C, E, D, and then back to A. So a circuit means I would have to go all the way back to the beginning. Did I cover all the places? Did I deliver all the pizzas? Sebastian, did I deliver all the pizzas on my route? Yeah, good. So as I label it, again, A, I went E, B, now I can't even see what I did. C, gotta be D, right? Yes. There we go, D, and then A. There we go. So you can tell it just by looking at my letter combination there. You could tell that this has to be a circuit because the beginning letter and the last letter are all the same. That helps me out, right, AJ? Good. So if you're going through and doing this and actually having trouble with this, go grab a highlighter, grab a colored pencil, and just trace it out as you go so you can make sure you see everything. And as we're writing this down, I highly recommend, especially when we're trying to map it out, put the number next to it, the pathway that we go. Now, it says right here, Hamilton Path circuits, a complete graph is a graph that has an edge between each pair of its vertices. Each pair of vertices. It says right here, AJ, not to fall asleep during my class. Now, is this first one right here, it's missing an AD, right? Yeah. It's missing a BC, right? Okay. Now, can anyone tell me why the second one over here is not? Tell me it is not a complete graph. Can you tell me why this second one is not a complete graph? What you got, Christopher? By the definition, there's got to be a connection everywhere, right? What's not connected? Vertices. Which ones? This one. A to what? A to D. No, I'm looking at this one right here, right? A to where? A does go to E. Is every vertice connected by a straight line? No? Which ones are not? Sebastian? E and B. A to what? A and D. Right here they are. There is a blue line here. But I'm trying to show you this one says it is complete, but this one is not complete. A to C, I heard it. A to C. Right here. So this is, okay, this is Kermit. He's trying to go over to Bob's house, but he doesn't want to stop over here. Okay, he doesn't want to stop to go say hi to Gerness because he wants to skip her house. So we need a road that goes directly from A to C. Now, is there another one? Now that we see what happened there, what else is missing? B to D. Thank you. B to D is also missing there. So each one has to be directly connected for it to be complete graph. A complete graph. That's the vocabulary for that one, a complete graph. So, and needed to there. Now, N, so the number of Hamilton circuits in a complete graph is n vertices, which is n minus 1 factorial. N stands for how many vertices I'm using. Number of vertices, right? Good. Factorial, n minus 1, we do the math on the inside, and then factorial means we're going to take that number and multiply by all the previous numbers. So if n equals 6, my formula would be 6 minus 1 factorial, which is 6 minus 1 is 5, right? 5 factorial, so that's 5 times 4 times 3 times 2, technically times 1, but we could forget the times 1. Because anything times 1 is the same thing. It doesn't change it if I multiply times 1. So that's what a factorial is. It is on your calculator. There's an exclamation mark. You could actually put it there. Now for this one, we are only dealing with 1, 2, 3, 4 vertices. 4 vertices. So I'm going to go through and look to see. So for this one right here, it says In a graph, there are edges between each pair of vertices, thus the graph is complete and has a Hamilton circuit. One circuit is A, B, C, D, A. A, B, C, D, A. Any circuit that passes through the same vertices in the same order will be considered the same. So now, if you notice, if I start at A and went B, C, D, then back to A, that's a circuit. It would mean exactly the same thing if I started at B. I would have went B, C, D, A, B. Those are the same orders, going all the way around, because the circuit just happened in the same order. A different circuit would mean I would actually, instead of going to go, who am I going to go pick up? So we got Bob over here, right? Bob is going to go to AJ's and then go to Kermit's, but sometimes he's just going to go to Kermit first and then go pick up AJ. Does that make sense? So it's a different order. It's a different combination. Depends on who Bob picks up first. Yes? Maybe? Okay. It'll make more sense here in a moment. Here's some math. Yep. Here's the math. Here's the math. If there's 4 vertices, it's always 4 minus 1, which is 3 factorial. So that's 3 times 2 times 1, which is 6. That's where I get that from. And I'm going to show you how to list all possibles, because that's going to be one of the test questions you guys are going to have to do coming up here soon. So we have A, B, C, D. We're going to start with A, and then we're going to go to B, and then C, and then D, and then back to A. So this is a circuit because this is going to go all the way back to the end, right, where I started. Now, this is super important to actually pay attention. This is the pattern. Not for you to be scrolling with your phone right now. No matter how boring I am, try not to fall asleep. Okay? Try not to fall asleep. You got this. Okay? Now, we went. Actually, let's do this one. I went A, B, C, D, A. Now, the next one, I'm going to change just one thing. I'm going to go A, B. So I'm going A, B. And instead of going to C, what could I do? I can go to D, C, A. D, C, A. So you notice the combination changes, but the first 2 letters are going to stay the same. And I just flip these 2 right here, right? Okay, so now since there's only 2 being flipped, I have that one and that one for both of those. Now I'm going to change it up again. So instead of doing AB, let's go AC and see what combinations I have. So if I go AC, what's the combinations I would have? I can go to B, D, then A. But now let's, another one for going AC. What's a different combination I would do for AC? AC, go D first, right? Go D, then B, and end at A. All right, so I got all those. Now let's go ahead and, so if I'm starting at A again, what's the direction I didn't go yet? AD. Very good, AD. So I'm going to go AD first then. So if I'm going AD first, A, D, what's the combination? I can go C, B, A, C, B, A. And then my last combination, A, D, B, because I'm just switching these two here, right? B, C, A. And how many did we end up with here? I got 6. It's almost like I have a math equation that goes along with that. With our 4 vertices, with a connected graph, I'm going to have 4, okay, which is my n minus 1. That's where I got this right here. This tells me I'm going to have 6 different combinations there. All right. Now, a complete graph, that's one that everything is connected, whose edges have numbers attached to them, is called a weighted graph. This is actually done quite often, especially when you're buying an airplane ticket. You're going to go from here to somewhere else, and usually they have these things called layovers. So you're going in multiple routes, right? When you go on vacation, you're going to go. The order that you go to those cities is important because sometimes you're going to have cheaper or more expensive routes for each one. Number long shows the edges if a weighted graphic called the weights of the edges. So we have weights on each one, which is normally a dollar amount or a distance, which you're trying to either minimize or maximize. Okay, information here. The graph below is a model for one-way airfares for cities for A, B, C, D. Use the weighted graph to find the cost of the trip for the Hamilton circuit of A, B, C, D, A. Let's see. Starting at A, I went to B. I went to C, D, A, right? Now, how would I figure out the cost of each one? Add them up, very good. That's all I have to do. So add them up. So my first plane ticket was $190. Second one, very good. Next one is $179. Last one is $157. Add those together, and that's going to be the cost of this trip. This is the video, okay? All right, so now we will continue. There we go. All right, starting again. All right, so now, did you add all these up? Yep, what did we come up with? 652. 652? Okay, so 652, that's it. That's going to be the cost of all these trips. Now, let's say, for instance, the brute force method is traveling salesperson. We are going to go through and problem is finding a Hamilton circuit in a completed weighted graph for which the sum of the weights of the edges is a minimum. Minimum meaning the smallest amount. I want the smallest number by doing the same thing. Such a Hamilton circuit is called the optimal Hamilton circuit or optimal solution. One method for finding this is the brute force method. Since we had 4 of these, I'm going to show you here. We already went through and found each one of the different 6 combinations, right? So all we have to do is go through and connect each one. So the route from A to B, B to C, C to D, D to A. And then using brute force, you're going to have to list each one. Yes, it is a lot more work. This is a pain. But it guarantees you that you have the optimal, the cheapest. Optimal solution right here, if Edgar is paying attention. Right here, right? Smallest numbers. Oscar, are you paying attention again? Yeah? Is that your phone in your hand again? That's not, yeah, it's not your phone, it's your pencil, right? It's a new mechanical pen. Yeah, okay. All right, so right here I have two that are the same value, which is most optimal. So I would take one of these routes right here, which is going to save me about 80 bucks just by doing this. So it's really important to actually be able to do this. Now, brute force method kind of sucks. It's a lot more work, but it guarantees the right answer. Another method is called the nearest neighbor. The nearest neighbor is I go from my starting point and I always take the cheapest value or the smallest number. I can't go back to a city twice, or I can't go back to a vertices more than once, right? And I can't go back to the end until, since it's a circuit, I have to go back to the end, the very last thing. So that's what this actually says. Model it, weighted graph, identify vertices, starting point, all this stuff right here. What I have here for you is a larger version. So starting at A, so we're going to go over this one right here. Starting at A, the smallest number from A is 114, right? So that's the reason why. So it's either 180, 114, 147, or 128. So nearest neighbor, you always take the smallest to 114 right here. All right, I can't go back to A, so that means I have to look at what's remaining. Is it 116, 115, or 169? 115. So yes, it's already red, but that's why we're choosing this right here. There we go. And now let's look to C. So I can go 128, 195, 194. Not 128. Why not 128? I can't go to A yet, right? Yeah. A has to be the last place that I go. And so I'm only looking at 195 or 194. And so I have to use that. So it's going to be, I have to take the 194 there. That's why that's important. And now from D, I can only go to two different places. I only go back to A. I can't do that yet, right? Because I still got to go to B. So that leaves me only one choice. I have to take the 145, and then my last is the 180. So step by step, that's how it needs to go. So optimal, this is just the nearest neighbor. It's not the most economical though. So I went A, C, E, there we go. And what is the cost on this one? $7.48. Now, I got a bag of chips for anyone here. I guarantee you right now that there is a better value. There is a better value. And since I am recording this, I'm going to stop before we actually get to the answer here. I got a bag of chips for the first person that can tell me what the better value in that route is going to be. So other than that, make sure you like, share, and subscribe. Support my channel.